Welcome to day 2 of 2.2 Polynomials of higher degree. We're going to look at graphing polynomials based off the leading coefficient test and finding their zeros, as well as taking a look at multiplicity of zeros and identifying what that means. Let's get started. To begin with, we're going to talk about the idea of a repeating zero, which is also known as multiplicity. And the multiplicity is referring to essentially the degree of a factor. So for a polynomial, if we have a factor of x minus a to the k power, where k is greater than 1, then we have a repeating zero at the x value of a. So if our factor has an exponent, then it has a multiplicity. And depending on that multiplicity, whether it's even or odd, it's going to dictate the behaviors of our graph at that value. If we have an odd multiplicity, so if k is odd, the graph is going to cross through the x-axis at that number or at that factor. So this is going to be like a cubic function where it crosses the x-axis, or even a linear function that crosses through. If instead we have an x value that is even, a k value that is even, so a multiplicity that's even, we're going to see the graph touch the x-axis but not cross through. So this is where you have more of a parabola, where it comes down, touches the x-axis, but then comes back up, so it never actually crosses. All right, we're going to go ahead and sketch the graph of our function, and we're going to do that by applying our end behavior, which is using the leading coefficient test. And then we're going to find the real zeros by factoring and finally draw a continuous curve through the information that we have. So for our starting function, we have negative x to the fourth plus x squared. For my end behavior, using my negative x to the fourth, I notice that I have a negative coefficient and I have an even degree, which tells me that on the left, my function is going to fall, and on the right, my function is going to fall. And again, it's going to be falling on both sides because I have a negative even function. To find my zeros, I'm going to go ahead and start by setting my equation equal to 0. And then I'm going to factor. I'm going to start by factoring out my greatest common factor. So I'll take out a negative x squared. And then I'm left with a positive x squared minus 1. And this all equals 0. I'm now going to set each one of my factors equal to 0. So I have negative x squared is equal to 0. And then I have x squared minus 1 is equal to 0. To finish solving, I'm going to multiply by a negative 1 on my first factor here. So I get x squared is equal to 0. And I'm going to leave it like that for right now. And then for my second equation, I'm going to add 1 to both sides. And then I'll take my square root. And I can't forget to add in a plus or minus. So I know for sure I have a 0 at 1 and I have a 0 at negative 1. So I'll put my two x-intercepts there. For my x squared equals 0, I notice that I have a even multiplicity for this factor. So I am going to take a square root to finish solving this. And normally I would say something like plus or minus 0, but since it's just 0, I don't need to factor in that plus or minus. So I'm going to get rid of that real fast. So I have just x equals 0. But the fact that I had an even multiplicity here tells me that my graph's going to act a little differently than it normally would. So I'll put another dot at 0. Okay, so I have a lot of things going on here. I know that it's going to fall on both sides. I know that I have my x-intercepts, and I also know that I have an even multiplicity for 0 and have an odd multiplicity for plus or minus 1. So at my plus or minus 1 values, I know my graph is going to cross the x-axis, but at 0, because it had that even multiplicity, it's going to bounce off. And that helps me to kind of sketch out my graph here. So I'm going to cross through at negative 1, bounce off at 0, cross through at positive 1. And again, I know I have to go down on both sides. And you can see that we have a rough sketch of our function using, again, our end behavior or leading coefficient test, and then also using the multiplicity of our zeros. Here we have another example. We're going to walk through the same process. We're going to go ahead and apply our end behavior leading coefficient test. We're going to find our zeros by setting it equal to 0 and factoring. And then we'll draw a continuous curve through the information we've graphed. For my end behavior, I noticed that I have my largest exponent of 3. So I have a positive odd function. It's positive because my coefficient is a positive 2, and it's odd because it has an odd degree. So since I have a positive odd function, and on my left side, the function is going to fall, and on the right side, it's going to rise. To find my zeros, again, I'm going to set my function equal to 0. I'm then going to go ahead and factor out the greatest common factor. In this case, it's going to be 2x squared. And I'm left with x plus 7. I can now take each one of my factors and set them equal to 0. and I can finish solving. I'll divide by 2, and then I'm left with that familiar factor of x squared equals 0. Again, this tells me that I have a multiplicity of 2 for this factor, even though I solved to get just 0. And then for my other factor, when I solve that, I get x is equal to negative 7. Okay, so I'm going to graph my x-intercepts. And again, I had an odd multiplicity because I had a single x plus 7. So I'm going to cross through at negative 7. And then at x squared, I have an even multiplicity, so I'm going to bounce off of that. So I'm going to go ahead and cross through at negative 7, go up to 0, bounce off, and rise again. So you can see that I am falling on the left, rising on the right. I bounced off at 0 because we had an even multiplicity for that factor. And then I crossed through at negative 7 because we had an odd multiplicity there. Now we're going to try and go backwards. I have the multiplicity for different zeros. I'm going to use that to help me write them as factors and then multiply everything together to help me go ahead and find my equation. Starting with the negative 1/2 that has a multiplicity of 1. And again, our multiplicity values are kind of like exponents for our factors. So I'm going to go ahead and write this as x minus a negative 1/2, which makes it a plus. And it is to the first power because my multiplicity is 1. And I don't really like dealing with fractions, so I'm going to multiply both those terms by 2 to turn this into a 2x plus 1, again to the first power. For my next factor, I have a 0 at 3 with a multiplicity of 2, so I'm going to write that as x minus 3 squared. Again, our multiplicity is the degree for our factor. I'm going to go ahead and square my x minus 3. So I have 2x plus 1, and then I have x squared minus 6x plus 9. And then if I distribute everything, I have to multiply 2x by all of my terms. That's going to get me 2x cubed minus 12x plus 18x. And then when I distribute the 1, we get plus x squared minus 6x plus 9. I can now go ahead and combine all my terms, so I end up with 2x cubed minus 11x squared. Oop, I missed an x squared up here. And then plus 12x, and lastly, plus 9. So this is my original polynomial that has a 0 at 1, sorry, negative 1/2 with multiplicity 1, and a 0 at 3 with multiplicity of 2. For our next example, we have a polynomial with zeros at 4, negative 3, positive 3, 0. And each has a multiplicity of 1. So again, that's going to be our degree for those factors. So I'm going to go ahead and write them as factors. We have x minus 4, x minus a negative 3, which will just become a plus 3, x minus 3, and lastly, x minus 0, which we're going to just rewrite as x. I'm going to start by multiplying x plus 3 and x minus 3 together because that's the difference of squares. And I end up getting x squared minus 9. And then if I multiply my x and my x minus 4 together, then we get x squared minus 4x. I'm going to go ahead and continue to distribute. So I have x squared times x squared, which is x to the 4th, and then minus 4x cubed minus 9x squared plus 36x. And I'm actually done because I can't combine any terms, and this is already in descending order. So I have my polynomial that had zeros of 4, negative 3, 3, and 0, all with multiplicity 1. And for our final example here, we're going to do this one more time. So we're going to rewrite this as factors, and then we're going to go ahead and multiply it all out. I have zeros at negative 3, positive 3, 2/3, and they all have multiplicity of 1. And then I also have a 0 at 0 with a multiplicity of 2. So if I write these as factors, it's going to be x minus the value, so x minus the negative 3, which will become plus 3, x minus 3, and x minus 2/3, all with multiplicity of 1. And then finally, x minus 0 squared. I'm going to apply a similar trick here with this term because I don't like fractions, so I'll multiply each of those by 3, which will give me 3x minus 2 times x squared. And then if I multiply the x plus 3 and the x minus 3 together, just like we did with the last example, we get x squared minus 9. So I'm going to go ahead and distribute over on this side here, which means I have x squared minus 9 times 3x cubed minus 2x squared. And then if I go ahead and do some distributing here, we get 3x to the 5th minus 2x to the 4th minus 27x cubed plus 18x squared. And I have my final answer there. All right, guys, that's going to do it for our notes. Go ahead and get started on the homework, and good luck.